Hello and welcome back to Calculus 2, Math 112. Today's lecture, number 11, is on L'Hopital's rule. L'Hopital's rule is a very important rule in calculus which allows us to calculate limits. We can evaluate limits of fractions that do not appear to be well defined or exist because we obtain 0 over 0 or infinity over infinity. And L'Hopital's rule allows us to calculate this limit. Now here is the basic statement of L'Hopital's rule. Suppose that f of a equals g of a, which equals 0. And f prime of a and g prime of a exist, and g prime of a does not equal 0. Then the limit as x approaches a of f of x over g of x equals f prime of a over g prime of a. This is L'Hopital's rule. It also works if we're approaching a and f of a and g of a are both infinity. So we have a stronger form of this rule. The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. And that is true when f of x and g of x both approach 0 as x approaches a, or f of x and g of x both approach infinity as x approaches a. This rule is stronger because it implies that we can continue to take derivatives sequentially until we arrive at a limit. So we can differentiate as many times as we wish until we reach a point where the nth derivative of f and the nth derivative of g give us a limit, and the nth derivative of g is not 0. Now let's take a look at a few examples. Suppose we're interested in the limit as x approaches 2 of x minus 2 over x squared minus 4. If we substitute in the value x equals 2, we get 2 minus 2 over 4 minus 4, which is 0 over 0. Since we get 0 over 0, this function is a candidate for L'Hopital's rule. So we can write the following. The limit as x approaches 2 of 1 over 2x. And if I let x equal 2, I get 1 over 4, 1/4. So you see we find this limit by taking the derivative of the numerator, which is 1, and then the derivative of the denominator, which is 2x. And then I substitute x equals 2, and I get 1/4. I'm able to find this limit by using L'Hopital's rule. In this particular case, I can check my answer because I know that the denominator, the original denominator, x squared minus 4, factors into x minus 2 times x plus 2. So what I really have is the limit as x approaches 2 of 1 over x plus 2, which once again equals 1/4. So this particular limit could have been evaluated by using algebra and factorization. We've done these in the past, but we can use L'Hopital's rule now and see that it's a very quick way of obtaining the correct answer. Now here is a very good example, a polynomial over a trig function. We have the limit as x approaches 0 of 8x squared over cosine x minus 1. If we substitute in x equals 0, we get 0 over 0. So we apply L'Hopital's rule. We say that this limit equals the limit as x approaches 0 of 16x over negative sine x. I took the derivative of the numerator, and then I took the derivative of the denominator. Now, once again, I get 0 over 0. I could take the derivative again using the stronger form of L'Hopital's rule, which would give me 16 over negative cosine of x. And the answer when x approaches 0 is just negative 16. What I did, though, was I even skipped that second differentiation, and I used the fact that I know that the limit as x approaches 0 of x over sine x equals 1. So the answer is negative 16. Here's another interesting example. Suppose that we look at the limit as t goes to 0 of sine 3t over 7t. That's the limit as t goes to 0 of, well, since I get 0 over 0 originally, I can use L'Hopital's rule. The derivative of the numerator is 3 cosine 3t, and the derivative of the denominator is 7. So as t goes to 0, cosine 3t goes to 1, and the answer is 3/7. Before I knew L'Hopital's rule, the way I would have solved this problem is to write my expression as the limit as t goes to 0 of sine 3t over 3t times 3/7. And that would have given me 1 times 3/7, which is 3/7. So I get the exact same answer when I use L'Hopital's rule. Now here's a good example of the application of L'Hopital's rule on a limit which requires repeated application of the rule. Suppose we're looking at the limit as x goes to infinity of the natural log of x plus 1 over the log of x to base 2. This is the limit as x goes to infinity of the natural log of x plus 1 times the natural log of 2 over the natural log of x. That's just using the identity. The log of x to base a is natural log of x over the natural log of a. Now, once again, we're going to apply L'Hopital's rule for the first time now, and we get natural log of 2 over 1 times 1 over x plus 1 divided by 1 over x. If we simplify this compound fraction, we get natural log of 2 times x over x plus 1. Once again, we still get infinity over infinity, so we differentiate one more time, applying L'Hopital's rule a second time, and we get natural log of 2 times 1 over 1. So the final limit is the natural log of 2. Now we look at our final example. The limit as x goes to infinity of the natural log of 2x minus the natural log of x plus 1. The first thing we do is write it as the limit as x goes to infinity of the natural log of 2x over x plus 1, because infinity minus infinity is undetermined. It's an indeterminate form. So that's why we have to write it this way. Then we can say that the natural log is a continuous function, so as x approaches infinity, the limit as x goes to infinity of this natural log function is the natural log of the limit of the function. 2x over x plus 1, we apply L'Hopital's rule, gives us 2 over 1. So it's the natural log of 2. The other way to look at it is that this is the limit as x goes to infinity of the natural log of, divide numerator and denominator by x. we get 2 over 1 plus 1 over x. As x goes to infinity, 1 over x goes to 0, and once again, our final answer is the natural log of 2. We'll see additional uses of L'Hopital's rule in future lectures. Thank you for joining us.
Right.